So last class we ended at addition and subtraction operations only, and more importantly we learned about geometrical significance of modulus and how do we see argument of z1 minus z2. So those were the two important things that we learned in the last class. Today I'm going to again start with one more operations on complex numbers, which is multiplication of complex numbers. Multiplication of complex numbers. Okay. So first I'm going to take up a very quick operation when you're performing multiplication on two complex numbers which have been written in point form. So let's say Z1 is a complex number which is given by A1 plus IB1 and Z2 is a complex number which is given as A2 plus IB2. Okay. So when you multiply two complex numbers, there is no restriction like real will multiply to real and imaginary will multiply to imaginary. Here multiplication will happen between every other term. So A1, A2, A1, A2, then you'll have I B1, A2, then you will have I A1, B2, then you will have I square B1, B2. Okay. Normally we write the real terms together, we write the imaginary terms together. So the real term is the first one and the last one. So it's A1, A2. I square we all know is -1. So it's minus B1, B2. And if you take an I common, it becomes A1, B2 plus A2, B1. Now this operation is very dry. That means it doesn't give us any kind of an insight as to what is happening when you're multiplying two complex numbers. Neither does it help us to figure out what is the position of the product Z1 and Z2 on the Argand plane if you know your Z1 and Z2 positions. Okay. So we'll take this operation, the same operation, when the complex numbers have been represented in the polar form, or for that matter in the Euler's form. We'll see in polar form or the Euler form, do we get an idea as to what is happening geometrically to these complex numbers to obtain the product of the two complex numbers. So here I will just write a short caption over here, point form multiplication, point form. Now let's do the same operation when they have been written in the polar form. So in polar form, let's say I have a complex number Z1, which is written as R1 cos theta 1 plus I sin theta 1. And Z2 is R2 cos theta 2 plus I sin theta 2. Okay. So when you multiply these two complex numbers, see the process is not different. Process is the same as what we took in the point form, but the outcome of it is slightly more appreciable. So when you multiply it, we get R1, R2. Okay, now I'll do the multiplication here itself. So cos theta 1 multiplies with cos theta 2 to give you a real part. So I'll just write down the real parts. I sin theta 1, I sin theta 2 multiplies to give you minus sin theta 1, sin theta 2. Remember again, I square is -1 plus I times cos theta 1, sin theta 2. Let me write it in white. Cos theta 1, sin theta 2. And we'll have sin theta 1, cos theta 2. Sin theta 1, cos theta 2. Now, those who have done trigonometry, in fact, all of you have done, would know that this is nothing but it's a compound angle expansion for cos of theta 1 plus theta 2. And this is a compound angle expansion for sin theta 1 plus theta 2. Now, here you go. This is a very useful information. So I come to know that I get a complex number whose argument is this, and sorry, modulus is this, and argument is this guy. So let me call it as phi for the timing. So if you write it as r cos phi plus I sin phi, you very well know that the argument and the modulus that you get are very much related to the argument and the modulus of the given two complex numbers. So just to summarize here, your modulus of Z1, Z2, which is actually your R, is nothing but the product of the moduli of Z1 and Z2. This is a good information for us, right? Because it will tell us what is the position of the product of the two complex numbers. Not only that, it also tells us that the argument of Z1, Z2, which is actually your phi in this case, is the sum of the arguments of Z1 and Z2. So I can write it like this. Correct? Very, very useful information. And we are going to, Akash, you missed 5 minutes of class, dear. Anyways, we are on the first slide only, don't worry. Okay, so please take some time to copy whatever has been written on the screen. So these two are very important information for us because they will help us to know what is happening in the background when you are multiplying two complex numbers. So first make a note of this. Dear all, please do not join late. As I already told you, I'm very particular about the time. Okay, I can end the class early, but I will never start the class late because I respect the time of people who join in early. Okay, in some countries, if you, for example, it's in Japan, I believe. If you come 1 minute late also, or let's say once few seconds late also, they basically count that number of seconds for the in times the total number of people attending. So you have wasted that much time. Okay, so let's say 100 people are attending a session and you come 1 minute late, means you have wasted 100 minutes. No, it's not for you, Akash. It's for anybody who has joined in late. Okay. All right. So now this rule can be extended. This rule can be extended. And I can safely say that if you have multiple complex numbers Z1, Z2, Z3 till Zn, and if you're taking the modulus of it, it is the product of the moduli of all these complex numbers. Okay, very important. And even for the arguments, if I have product of Z1, Z2, Z3 till Zn and I'm finding its argument, it is the sum of the arguments of each of these complex numbers. You say, sir, it's very much like the log property. The arguments very much follow the log property. Yes, of course. One thing that you have to keep in mind is that when you're adding multiple arguments, there may be cases that your result may exceed minus pi to pi. So if somebody is asking the principal argument, make sure you put this result within the required interval of minus pi to pi. Okay. In case somebody wants you to write the principal argument. Is that fine? Now we'll see what is basically happening to the location of Z1 and Z2 when we know Z1 and Z2 location. So see what is happening. If let's say somebody gives me the position of Z1, let's say Z1 is here, okay, and somebody gives me the position of Z2, let's say Z2 is here, okay. So let's say this distance, let me make it in white, this distance is R1, okay, this angle is θ1, and let's say this is R2, and this is θ2, okay. So where is Z1 into Z2 located? How will you figure it out? So the previous discussion that we had will help us to figure out where is Z1 into Z2. So what it says is that figure out a complex number which is located at θ1 plus θ2. Figure out a complex number which is located at an argument of θ1 plus θ2 and it is located at a distance of R1 into R2. So what I will do is, I already know θ1. Okay, so from here I will make θ2. Okay, so from here I will add θ2. Let me write it in some other color, else you will get confused. θ2. Okay, and I will make I'll make a length, and on that length, basically I will cut R1 into R2 length. So product of R1 into R2. And there you go. At this point, I hope you can see it. At this point, your Z1 into Z2 will be located. Right? So in short, what are you doing? You are taking Z1. I hope you can see my photo in the video. Take Z1, rotate it. Rotate it by how much? θ2. correct? Theta 2 is the argument of Z2, correct? And scale it up or down, that depends upon R2. So scale it by a factor of R2. Are you getting my point? So whatever point you get, that point will be your Z1 into Z2. So because of that polar form representation, and you can see even in Euler form, we'll get the same thing. We are able to figure out that, oh, this is our location of Z1 into Z2. Point form was not giving us any kind of an insight. Point form was waste. Okay, is this fine? Any question related to how do you locate Z1 into Z2? I'm repeating it again. Take this, I'll just name it. I should name it in different color. Let's take OA. Okay. And OA, you rotate further by theta 2. Which direction? Theta 2 anti-clockwise direction. Correct? Now, that is actually decided by what is your theta 2. If your theta 2 was a negative argument, then the same would be getting rotated clockwise by theta 2. So what I'm saying, rotate it anti-clockwise by theta 2. If theta 2 is negative, then automatically that anti-clockwise will become clockwise. It's like saying add a -5. Because see, it's actually like subtracting -5, but you say add a -5. So subtracting 5 is as good as saying add a -5. So you are rotating it by theta 2 anti-clockwise, and you are scaling up the modulus by a factor of R2. Now scaling up or down, that depends on R2. Whatever is R2. R2 may be a fraction also, right? So fraction means you'll be reducing it. So I'll take an example. Let's say your Z1 was 3e to the power I pi by 3. Okay. And Z2 was 1/4 e to the power I pi by 6. Okay. So when you multiply Z1 into Z2, what do you get? You get a complex number whose argument would be pi by 3 plus pi by 6, which is pi by 2, and modulus will be 3 into 1 by 4. So it will be 3 by 4 e to the power I pi by 2, right? So what you did, I'm just going to draw it in a very small version. So this was your Z1 earlier. Okay, this angle was 60 degree, pi by 3 you can say. Okay, and this distance was 3 units. So when you multiplied it to Z2, what you did? You further rotated it by 30 degrees. So you further rotated it by 30 degrees. So you came on this line, which is your imaginary Z-axis line, and your modulus became 3 by 4. So it became shorter in length. So this is just 3 by 4. So this point is your Z1 into Z2. Getting the point here? This is something which is very important. JEE will ask you a lot of questions based on this concept. Now, one interesting thing I would like to show here. Somebody figured out that you can actually make this particular point from this simple construction. So all of you please watch out this. Let's say I complete a triangle OAP. Okay, what is this P? P is a point which is 1, 0. By the way, let me erase other things which are not required. Okay. And he also figured out that this triangle OBC, so OAP and OCB, these two triangles are similar. Okay. So this is, you can say, a geometrical connection between these two triangles. So a question can be framed on this. Now you must be wondering how it is similar. How it is similar? I'll show you how it is similar. See, first of all, if this whole angle is theta 1 plus theta 2, let me just show you. If this whole angle is theta 1 plus theta 2, until here it is theta 2 only, how much is this angle? Sorry for drawing such a big angle. How much is this angle? You say theta 1, correct? Yes. So this angle matches with this angle. Okay. So this is an angle matching doesn't make it similar. Okay. Let me show you something else here over here. See here. If I take if I take the ratio of two sides, let's say I take OA by OP. If I take OA by OP, what will I get? What will I get? OA is R1, OP is 1. I will get the same answer if I do OC by OB. So OC is R1, R2. Let me write it over here first. OC by OB. OC is R1, R2 and OB is R2. R2, R2 gone, same thing, R1. Okay. So this is another, you can say, visual representation of the idea of multiplication of two complex numbers. So questions can be framed in so many ways. You should be ready with all your insights and your visual representations. So please copy this and we'll take a question on this. Acha, by the way, some people are asking, can you show this on the Euler's form? See, on the Euler's form, it is even simpler. Just a second, guys. Yeah. In the Euler form, it is even simpler. If you have Z1 as R1 e to the power I theta 1 and Z2 as R2 e to the power I theta 2, if you multiply it by the virtue of the fact that they are written in exponential forms, it becomes very easy for us to realize that, oh, I'm getting a complex number whose modulus is the product of the moduli of Z1 and Z2 and whose argument is the sum of the moduli of Z1, sum of the arguments of Z1, Z2. Okay, so Euler form is a miraculous form. It helps us to know the geometrical relevance of this operation. Okay, so we'll take few questions based on this. Let's take a question. Okay. Find the area of the triangle whose vertices are Z, IZ and Z plus IZ. Find the area of the triangle whose vertices are Z, IZ and Z plus IZ. Guys and girls, you don't need any kind of mathematics for this. It's just the visual representation that will help you to solve this. Sorry, I missed out the question. Madhav, can we change the scale of the graph and then multiply? Madhav, did you get that answer while I was explaining it? Or do you want me to explain it? Okay. Yeah. See, let me put the poll on in case you have solved it. I would love to see your response. Again, people are joining late. As I told you, till further announcements, the classes will start from 3:45. Even in the reminder, it was written. Even in the class timing, it was written. And then again, it was written that join at 3:45. Very good. I'm getting responses. This is under a minute question, guys. Just a minute is what you're going to take for solving this question, not more than that. If you know your basics of geometrical understanding of these operations, you can do it in one shot. Okay, let's end this poll in another 20 seconds. So those who want to answer, please do so. Okay, 5, 4, 3, 2, 1, go. All right. So I can see response coming from almost 20 of you. Most of you have gone with B. Option number B. Let's check. See, let me assume Z to be anywhere. Let's say I take Z over here. It's my call. Okay? I'm taking in the first quadrant. So this is the location of Z. Where will be the location of IZ? Now IZ is like you're multiplying Z with I. Are you getting my point? Okay. So wherever is Z located, let's say Z was located at a distance of R and at an angle of theta, you need to rotate it by an angle anti-clockwise, which is the argument of I. So argument of Y, whatever is this angle, you have to rotate that line anti-clockwise by that angle. Correct? And you need to scale it up by the same amount or by the same factor as the modulus of I. Modulus of I is 1, so you don't have to scale up or down. Length will remain the same. Only rotation will happen. So Madhav is correct. Just rotation will happen. Rotation will happen by an angle of how much? Same as the argument of this complex number. We all know I is having argument of 90 degree. So I'll rotate it by 90 degrees. So this is how rotation will happen. So I'm trying my best to make a 90-degree line to this. Okay, so this will be your IZ. Okay, so ZIZ located. Now Z plus IZ. Now I have to go back to my understanding of addition of complex numbers. So when we want to know where is Z1 plus Z2 located, what did we do? We used to make a parallelogram, right? We used to make a parallelogram like this. Tuck, 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 tuck. Sorry for going inside. So let me make it in blue color so that we can read it. Oh, sorry. I think I have made a bigger triangle. Yeah. Okay. So this is your parallelogram. By the way, this parallelogram will be a square. Why? Because this length and this length are same, and this is 90 degree. So will be this. This will be 90 degree, and this length will be also the same. So if this is mod Z, this will also be mod Z. In reality, mod of IZ is mod Z only, because you'll write mod I into mod Z. Mod I is known to be 1. So 1 into mod Z is mod Z only. So this length will also be mod Z. This length will also be mod Z. Okay. So here is our Z plus IZ. I hope you can see that in yellow. Now, what is my question asking? My question is saying that if I make a triangle out of these three vertices, that means Z, IZ and Z plus IZ, what will be the area of this triangle? Now, I think even a 9th grader can answer this. Half base into height. So half base is mod Z. Height is also mod Z. So answer is half mod Z square. So option number B is correct. You got it? Right? Most of us, when we learn complex number in the school, the first thing that we are taught is put Z as X plus IY. No need to do it. Of course, I'm not saying that should never be done. Wherever it is, desperately required, do it. But where you can solve a problem by geometrical interpretation, nothing like this. And that is what these exams like JEE, especially KVPY, JEE Advanced, they want you to, think about things geometrically. Okay, let's have another question. Let's have another question. Okay, I would like you to do this question. Now they have called it as a vector. Don't get confused. Complex numbers are position vectors only. Okay, just that you don't have an I and a J. Don't get confused. So I is your 1, J is your I actually. Okay, anyways, Z is 3 plus 4I and it is rotated at 180 degree angles in anti-clockwise direction. and its length is increased by 2.5 times. What will be the new position? Are you getting my point? So 3 minus 4i was a complex number. It is rotated 180 degrees anti-clockwise direction, and its length is increased by 2.5 times. So what is the new complex number? I will put the poll on. This is a very easy question. I'm sure all of you should get the right answer. Anybody who joined in now, because the count was one less till now. Anybody who joined in now, please message me personally that I joined in now, else you will be marked absent by mistake because I already took the attendance. Anybody? Not at 4. Somebody joined now, 4:11. 4:10 or 4:11. Just 1 or 2 minutes before. Okay, I'll come to know from the attendance, final attendance. Very good. I have got response from 3 of you. Guys, I think all the informations are given to you. You just have to apply it. Very good, very good. One of the options is leading. I will not tell you which one, else everybody will start pressing that only. Can we wrap this up in 30 seconds? Easy, easy. Come on, guys, come on. What, sir? You are cheering like you are in the cricket field. Okay, 5. Yes, why not, Madhav? Minus I is 1 by I. Absolutely. Why not? Okay, 5, 4, 3, 2, 1, fire. Okay. Most of you have gone with B. B for Bengaluru. Let's check. See, guys, rotating anti-clockwise and 180 degree and increasing the length by 2.5 folds basically is commenting that 2.5, that is 5 by 2, is the modulus of Z2. So let's say I call this as Z and Z1, whatever. And you have a complex number whose modulus is 5 by 2 and whose argument is pi. So if you want to write it, you can write it like this. Many people will say, sir, it is just minus 5 by 2. Yes, agreed to you. So your answer would be, your new location would be Z into Z2, which is nothing but minus 5 by 2 times 3 minus 4i, which is going to give you minus 15 by 2 plus 10i. Option B is correct. Okay. Janta who is answering with other options. Let me check. 8 of you gave a wrong answer. Why? Chalo, I'll give you one more chance. Meharbani sir, give us one more opportunity. एक गलती की इतनी बड़ी सजा सर मत दीजिए sir. How many of you know Hindi well? Okay. Next. Definitely not you. Don't worry, Charan. I never teach in Hindi. Next. A man walks a distance of 3 units from the origin towards northeast. From there, he walks a distance of 4 units towards northwest. To reach a point P, find the position of P in the Argand plane. JEE 2007 question, guys. JEE 2007 question. So you are looking at a question which came in one of the JEE exams. Poll is on. Let's do our best. Make a diagram first. We'll come to know. Good, good, good. One minute gone. I've got responses from 4 of you. Let's have last 30 seconds. Five, four, three, two, one, go. All right. Let's stop the poll. A very confused response. B, C, and D, almost the same number of votes I got. Okay. Let's try to discuss this. See, there's a man who walks 3 units along the direction of northeast. Northeast is this direction, so he walks 3 units along this direction. Okay, so we know that this is 3 and this is 45 degrees. Okay, now from there he walks 4 units towards northwest. So from here he starts going towards 4 units towards northwest. So let me just take a yellow line, and he goes 4 units towards northwest. Okay, this is again a 45 degree, you can say. Okay, this is 45 degrees, and this is 4 units. Okay, so from O he goes to a point, let's say intermediate point Q, and from Q he goes to P. Okay, now the question setter is asking you, this point P, what is the complex number representation for this point P? How will you find this out? How will you find this out? Yes. Any suggestions? Any suggestions here? Any suggestions? See, first of all, you know this is 90 degree. This is 90 degrees. Correct? This is what is required. Yes, of course. Of course. You can treat this as if you are adding two vectors. Correct. So this plus this is what is your this vector. Correct. So now, if you look at this complex, this vector, if you're looking at it from a vector point of view, this is nothing but, this is 3 by root 2 plus 3 by root 2 I. Am I right? Because this length, this modulus is 3 and the argument is 45 degree. So you can treat this complex number to be this. By the way, this can also be written as 3 e to the power I pi by 4. Okay, why I'm writing it as 3 to the power I pi by 4? Because I can see an expression like this sitting on the denominator, on the options. Okay, in all of the options it is sitting. Correct. Now what about this? What about this? This complex number has a modulus of 4. Okay, and what about the argument? What about the argument? Here the argument that you are going to write, this is your, yes, 135 degrees. So this is your e to the power I 3 pi by 4. Yes or no? Correct? Any questions here? Okay. So what are we looking for? We are looking for the sum of these. So your answer would be, or your OP would be nothing but 3 e to the power I pi by 4 plus 4 e to the power minus 3 I 3 pi by 4. Correct? Yes or no? Any questions here? Okay. Now what I'm going to do is, I'm going to write minus 3 I pi by 4 like this. I'm going to write e to the power 4 e to the power I pi minus pi by 4. Okay. Or you can write it like this also, no issues. We will write e to the power minus I pi plus I pi by 4. Okay. Just to make our life simple, e to the power I pi by 4, and this is nothing but 4 e to the power minus I pi into e to the power I pi by 4. Now, e to the power I pi by 4, if you take common, you will end up getting 3 plus 4 e to the power I pi minus I pi. 3 to the power minus I pi is actually how much? How much is that? Oh, sorry. I'm so sorry. Yeah. Thank you, Madhav. My bad. Yeah. Minus. I wanted to put a minus here. By mistake, I wrote, yeah, sorry. Is this fine? So then I have to break it like this. Sorry. Then I'll have to break it like this. I'll break it as 4 e to the power I pi by 2 plus pi by 4. Correct? So 3 e to the power I pi by 4 plus 4 e to the power I pi by 2 into e to the power I pi by 4. Take e to the power I pi by 4 common. You'll have 3 plus 4 e to the power I pi by 2. Remember, e to the power I pi by 2 is I. Okay. So this will give you 3 plus 4i, which I believe is option number D. Yes or no? This is your option number D. Let me see the response once again. D got the second highest vote, but many of you went for B. Why? Oh, okay. So this will be nothing but option number D. Is the idea clear? Anurag, I changed it. It was I 3 pi by 4. 3 pi by 4, I broke it up as pi by 2 plus pi by 4. This I again broke it up as e to the power I pi by 2, e to the power I pi by 4, e to the power I pi by 2 is I, okay, and e to the power I pi by 4 I've already taken common, and this is what I end up getting. Is the idea clear? Okay, so this is a simple question where you can use your vector fundamentals to solve this question rather than using your complex number fundamentals. Of course, both of them are the same things, but basically what helps you is more of a vector addition over here. Let's take another question. Let's have this question. Where is that gone? Question. Just a second, guys. Yeah. If A plus IB, C plus ID, E plus IF, G plus IH is equal to A plus IB, then A square plus B square, C square plus D square, E square plus F square, and G square plus H square is equal to which of the following options? Let us start the poll for this. It's a super easy question. If you have understood the multiplication process, you'll be able to answer this within 30 seconds. Awesome, awesome. I'm getting some responses. Let's close this in another 30 seconds. Dear all, it is super easy. Yes, absolutely, Anurag. Absolutely. Okay, 5, 4, 3, 2, 1, go. All right, most of you have gone for option number A. Okay, let's check. See, guys, here we are basically multiplying 4 complex numbers, isn't it? So Z1, Z2, Z3, Z4 are being multiplied. Okay, so can I say the modulus of this complex number is as good as moduli, product of the moduli of each one of them, isn't it? Correct. So A plus IB modulus is nothing but modulus of each one of them, that is A plus IB, small a plus IB, small c plus ID, E plus IF, G plus, oh sorry, G plus IH, correct? So under root of A square plus B square is nothing but under root of A square plus B square, under root of C square plus D square, under root of E square plus F square, under root of G square plus H square. Okay, so this is from that property which we had discovered while we were doing multiplication. So A square plus B square, if you square both the sides, that will end up giving you the expression that you actually require. So your answer will be A square plus B square. Option number A is correct. Right? So this was an important property for us, which helped us to find out this problem in a very quick time. Okay. So the next operation that we are going to talk about is division. Okay, so multiplication is done. Now we are going towards division. But before division, I would like to talk about conjugate of a complex number. This is a very important and interesting concept. Conjugate of a complex number. Conjugate of a complex number. Any complex number, if it is a plus ib, its conjugate is represented by a bar. Many international books will represent it as a star. And it is given by a minus ib. In other words, change the sign of I. Change the sign of I in the complex number. That's it. So for example, if you have z as 3 plus 4i, its conjugate will be 3 minus 4i. Okay. If you have a complex number 2 minus 3i, its conjugate will be 2 plus 3i. If you have a complex number which is 4i plus 1, then its conjugate will be what? What will be the conjugate of this? Many people will say 4i minus 1. No, it is minus 4i plus 1. Okay. Remember, you don't have to change the sign in between. That's what people think. You have to change the sign of I. Yes, correct. Okay. Now let us look into the positioning of the conjugate of a complex number. So what is the positioning of conjugate and how it is useful? We'll see in some time how the conjugate will be helpful. Yes, Madhav, absolutely. So if you see, you are actually changing the sign of the ordinate of that point, isn't it? So let's say Z was a point A comma B. Its conjugate will come in a position where you are changing the sign of B to minus B, isn't it? Changing the sign of I is equivalent to changing the sign of the imaginary part. So you are basically reflecting the complex number about the real Z axis. Okay. So this is the reflection. This is a reflection about the real Z axis. So this length will be equal to this length. Now, even though I'm showing it in the first quadrant, it doesn't matter wherever you take the Z. If you take it in the second quadrant, your conjugate will be in the third. If you take it in the third, your conjugate will be in the second. If you take it in the fourth, your conjugate will be in the first. In reality, both are conjugates of each other. Z and Z conjugate are conjugates of each other. Are conjugates of each other. So it's like saying object is the mirror image of the image, isn't it? Just like image is the image of the object, object is the image of the image. Okay. So let us understand few of the properties of conjugate and why it is so important to us. Let us look into that. Properties of conjugate. The biggest property of conjugate is if you multiply any complex number with its conjugate, it basically gives you a purely real quantity, which is mod of z square, or you can also write mod of z conjugate whole square. Both are same actually. Okay. So this is one of the most important properties. That's why before division, I thought I would introduce this concept to you, because when you are writing z1 by z2, we normally try to convert it to a point form by multiplying the denominator with its conjugate. Okay. So this is one of the most important property. You'll be using this very, very heavily. Okay. So please make a note of this. Z into Z conjugate is mod of Z square. How? The proof is very easy to understand, because if let's say Z is A plus IB, its conjugate will be A minus IB. Correct. So if you multiply Z and Z conjugate, basically you're doing A plus IB times A minus IB. So this will give you A square minus IB whole square, which is A square plus B square, which is nothing but mod Z square. Okay. Second thing is, as we already discussed, the complex number modulus and its conjugate modulus will be the same. It's obvious from this diagram also. Since they are mirror image, this distance, which is your mod Z, will be same as this distance, which is your mod of Z conjugate. Okay. So the modulus of Z and its conjugate is the same. The argument of Z and its conjugate are negatives of each other. This is very important. Now I'm talking about principal argument. Please note that I'm talking about the principal argument. I don't think so I have to keep repeating this every now and then. Unless until stated otherwise, I always will talk about principal argument only. So the argument of Z and its conjugate will always be opposite in sign. As you can see from the diagram also, if this angle is theta, then this angle would be negative of that theta. Now, it doesn't matter whether it is in the first quadrant or fourth quadrant or second quadrant or third quadrant, this property will be universally be applicable. So let's say if your Z was here, okay, then its conjugate will come over here. Okay, so let's say whatever angle it was making, just say hypothetically this was making, let's say, minus 135 degree. Okay, then this angle will be plus 135 degree. Okay, it will always be negatives of each other. Okay. If it is 180 degree, it will remain 180 degree. Okay, Pranav, that's a very good exception he has brought in. So if your argument is 180 degrees, then or you can say pi, let's not write it in degrees. So if your argument of Z is pi, then its conjugate argument will also be pi. See, the reason being, if a complex number is having an argument as pi, that means it is on the negative real Z axis. So let's say minus 5. Its conjugate will also be minus 5. Correct? So the argument of Z and Z conjugate would be the same. Okay. Same with 0 also. If it is 0, then it is the conjugate argument will also be 0. Even if you say minus 0, it is back to 0 only. Okay. But yes, pi is a very valid point brought by Pranav. Okay. Is this fine? Few other properties. I'll continue here. I think this was the third one. The fourth property is, if you add or subtract two complex numbers and take its conjugate, it is as good as adding or subtracting their respective conjugates. Okay. So when you add or subtract and then take a conjugate, it is as good as you are adding or subtracting their conjugates. Okay. Same goes with multiplication and division. If you conjugate the product of two complex numbers, it is as good as the product of their conjugates. Let me write it as A. And if you write the quotient of two complex numbers and take its conjugate, it is as good as the ratio of their conjugates. Ratio of their conjugates. Okay. Now, certain properties which will be very helpful later on. Z plus Z conjugate is twice the real part of Z. Okay, this proof is very easy. So if your Z is A plus IB, its conjugate will be A minus IB. So if you add both of them, don't you get 2A? So 2A means 2 times real part of Z. Okay, please note A is represented like real part of Z. This is something which you should all be knowing by now. A is real Z, B is imaginary Z. Okay, when I say imaginary Z, that doesn't mean it's an imaginary number. Both are real number only. It's just that they're called as real part and imaginary part. Okay, please recall this. Okay, so a corollary of this is, if Z plus Z conjugate is 0, it implies Z is a purely imaginary number. Z is a purely imaginary complex number. Why? Very simple. Because if your conjugate added to the complex number gives you 0, it means 2A is 0, it means A is 0. If A is 0 means there is no real part, and if there is no real part, that means the complex number is purely imaginary. Correct? This is going to be useful later on, so please make a note of that. B part of this property is, if Z minus Z conjugate is actually I times 2 imaginary Z. Okay? Again, simple. If you subtract it, if let's say Z is A plus IB, Z is A minus IB. If you subtract Z and Z conjugate, you get 2IB. You can write it as I2B. And I2B means I2 times imaginary part of Z. Okay. Now, a corollary of this is, if Z is equal to Z conjugate, or you can say Z minus Z conjugate is equal to 0. Let me write it in that way only. Z minus Z conjugate is 0. It means Z is purely real. Z is purely real. Right? Because imaginary part is 0. Imaginary part is 0 means there is there's no imaginary part in that complex number, only real part is there. So it's a purely real complex number. Is this fine? Somebody has joined in the session. Who joined in late? My God, people are joining as late as 4:40. Yeah, is there somebody who joined in late? Please let me know. I'll have to take the attendance once more. Yes, Anurag, I'll take you to the third point. This was your third point. Do let me know once you have copied. Okay. All right. Now, few misconceptions which I would like to address over here. Few misconceptions. Few misconceptions. I mean, I don't know from where these misconceptions arise. Many people think mod z square is same as z square. Number one. No. Okay. Mod z square is you are squaring the modulus of the complex number, which is going to be a purely real quantity. And z square means you're squaring a complex number, which will again give you a complex quantity. It's not that I'm not saying real cannot be equal to a real number cannot be a complex number, but this will always be real. And this may not be real. Are you getting my point? So mod z square is not z square. It is actually z into z conjugate. Okay. So please note this down. This is not equal to this. However, it is equal to this. Okay. Second misconception that people have is conjugate of a complex number is reciprocal of the complex number. No, this is not always true. This is true only when the complex number is unimodular. Unimodular means it has a modulus of 1. Okay, only then it is correct. Why? Because if it is unimodular, you can say this property will be true. Correct? And then only you can say z conjugate is 1 by z. So this is not always true. This is true only when it is unimodular. So what is the correct form of it? This is nothing but mod z square by z. This is the correct form. Okay. Please do not make such mistakes. In the previous few classes with the other batch, I was seeing people were making this mistake. Okay. So this is the correct form over here. Let me write it in white. So here, mod z square is z conjugate. This is the correct. Is that fine? Any questions? Any questions, any concerns? Do let me know. Okay. So let's take some questions. In fact, they're also part of the properties, but I would not take them as a property. I would take them as a question. Could you go to the sixth property? There you go, sixth property. Done, Madhav. Ten seconds, huh? You can take a snapshot. Sir, you write very fast, sir. We are not able to copy. Okay. Let's take a question come property. I mean, I'll call it as a property more than a question, because many competitive exams would require you to know it so that you save a lot of time. Yeah, this property says mod of z1 plus z2 square plus mod of z1 minus z2 square is equal to 2 mod z1 square mod z2 square. Okay. Now I may ask you to prove it. Okay. Let us prove it in two ways. One is mathematically and other is geometrically. Okay, so let's prove it mathematically first. So since this is a very first problem, let me do it so that you can understand the process. If you look at this term mod z1 plus z2 square, by the very definition of, or by the very property of conjugates, we learned that I can write it as z1 plus z2 into conjugate of z1 plus z2, isn't it? So think in your mind as if you have written mod of some complex number square. Isn't it equal to z into its conjugate? That's what I have written over here. Okay. Now, can I write the second term as z1 conjugate plus z2 conjugate? If you multiply, you get z1 z1 conjugate, you get z1 z2 conjugate, you get z1 conjugate z2, and you get z2 z2 conjugate. Okay, so this will give you mod z1 square, right? This will give you mod z2 square, and this will give you z1 z2 conjugate plus z1 conjugate z2. Now, dear all, I would like you to understand one more thing over here, even though it is not that relevant in the problem solving. This term that you see over here, it is actually the real part of, or you can say two real part of z1 z2 conjugate. You can also say z1 z2 z1 conjugate z2, both are fine. You can also write it as, this thing can also be written as 2, let me write it in white, 2 real z1 conjugate z2. Now why? Because if you see in reality, this complex number and this complex number are actually conjugates of each other, isn't it? So if you call this as z, let's say z, then this will be z conjugate. And didn't we see in one of the properties that z plus z conjugate is 2 real part of z? So 2 real part of this. Okay. So please keep this in mind. Similarly, without much waste of time, can I also say that the second term over here, which is mod z1 minus z2 square, can be written as mod z1 square mod z2 square you can say minus z1 conjugate z2 minus z2, sorry, z1 z2 conjugate. Correct? Same logic, right? This can also be written as, if you want, as negative of 2 real part of z1 z2 conjugate. Okay. Now let us add these two. If you add them, you would realize, you will have z1 modulus square coming 2 times. So 2 mod z1 square. You have z2 mod square coming 2 times. So 2 mod z2 square. And the negative 2 real part and the positive 2 real part will cancel each other out. That will give you twice of mod z1 square mod z2 square, which is your RHS, and hence proved. Okay. Is the approach clear how to prove it? One very important thing that we have to keep in our mind is this property. This property is very, very important. You never know where it will be useful for you in solving questions. It is used very, very widely. Very, very widely. Okay, very important property. Okay. Now, the same thing I can prove in a geometrical sense. No, Gayatri, do not apply scalar fundamentals to vectors. So don't apply your scalar concepts on complex numbers. It may help you to prove it in that way, but that is by luck or by chance you got the answer. It is not a plus b whole square, a minus b square. If it was that easy, I would not have asked you to do this question. Okay. Mod z1 plus z2 whole square, you cannot treat as if you are treating scalar quantities. See, this quantity itself is not equal to mod z1 plus mod z2. As we already discussed, it is only equal to it when the argument of z1 and z2 are equal. Okay. So when you're squaring this, you cannot treat as if you are squaring this. No. You are lucky enough if you got the answer in this case, but it may not be always the case. Do not do this mistake. I'm not asking you to do a plus b whole square and a minus b whole square. Okay, so by chance it will become correct here, but not always. Copied. Somebody was asking me to show this part. Done. Now the same thing actually can be proven in a very simpler way by a method which you learned in class 9th. What, sir? In class 9th we learned how to do this question? Yes, probably you are not aware that you were doing this question actually in class 9th. Okay, see how. How many of you remember this property? It's an R.D. Sharma question of class 9th. If you have an R.D. Sharma of 9th grade, you can open the chapter parallelograms. Okay, there is a property of parallelograms that the sum of the squares of the diagonal is equal to the sum of the squares of the sides of a parallelogram. This property is always true. So sum of the squares of the diagonals is actually the sum of the squares of the sides. AB square, BC square, CD square, and AD square. Do you remember this property? This is taught in grade 9th. 9th grade concept. How many of you remember it? Aditya remembers. Yeah, you have to prove it. This is a R.D. Sharma question of grade 9. So I remember long back, I think 7 or 8 years ago, I was trying to do this question with a 9th grader, and I told them, you will again see this concept in grade 11th when you do complex numbers, and they were like surprised. Okay. So now whatever you see here in this property is actually related to this theorem. You must be wondering how. Okay, let's say I consider this to be origin. Okay. And I consider this B to be Z1 point, and I consider D to be Z2 point. Then automatically C will become Z1 plus Z2. Correct? So we all know AC diagonal length will be mod Z1 plus Z2. And a BD diagonal length will be mod Z1 minus Z2. Okay. OB length is mod Z1. And OD length is mod Z2. And since it is a parallelogram, this will also be mod Z1 and this will also be mod Z2. Correct? So now AC square is nothing but mod Z1 plus Z2 square. BD square is nothing but mod Z1 minus Z2 square. And these guys are nothing but mod Z1 square, mod Z2 square, mod Z1 square, mod Z2 square. Okay. And that's nothing but the given property that we are given. Is this clear? Any questions? Any questions? Any concerns? Okay. Now, a more generic version of it is more generic version, or you can say in general. In general, AZ1 plus BZ2 mod square and AZ1 minus BZ2 mod square is A square plus B square times mod Z1 square mod Z2 square. It can be proved in a very similar way. Okay. Let's take more questions. Let's take more questions. Done. Note it down. Can I go on to the next page? Oh, I got it wrong. That's why. Oh, you made a mistake in class 9th also, Aditya. Huh? Okay, guys, one more important announcement. Any of your acquaintances who are looking for admission in class 11th or for that matter 9th and 10th, our admission process has started. Okay. So whether NPS or non-NPS students, so I'm talking about your juniors who will be coming in class 11th, do let them know so they can get in touch with any one of us, whether me, Dheeraj sir, Gaurav sir, or Tushar sir, if you have the number for the admission process. Or Pushpa Narayan. She is our coordinator. She has been also added to the group. Okay, so do let them know. All right, so next question. Next question is, if there are three complex numbers Z1, Z2, Z3, which satisfy the following property. Mod Z1 is 1, mod Z2 is 2, mod Z3 is 3, and mod of 9 Z1 Z2 plus 4 Z1 Z3 plus Z2 Z3. This is equal to 6. Then find the value of mod Z1 plus Z2 plus Z3. Then find the value of mod of Z1 plus Z2 plus Z3. Let's have 1.5 minutes for this question. Everybody please try this out and put your response on the chat box. Yes, any success? One hint I would like to give you all, if you see these numbers 9, 4, 1, they're actually squares of these quantities. That should ring a bell in your mind. Okay, Pranav, very good. Anybody else? Aditya, very good. Okay, let's do this. See, first of all, this expression itself, I will try to work on it once again. What I will do first, within the modulus symbol, I will take Z1, Z2, Z3 common from each one of these terms. So I'll get 9 by Z3, I'll get 4 by Z2, and I will get 1 by Z1. Okay, no doubt about that. Yes or no? Correct. And as per the modulus property, I can split this as modulus of this and modulus of this. Correct. Thanks to the modulus property that we can write this term as this. Right. Now, all of you please pay attention. You have been provided that mod Z1 is 1. So can I say Z1 into Z1 conjugate is mod Z1 square, which is equal to 1. So 1 by Z1 is nothing but Z1 conjugate. So this guy will become Z1 conjugate, right? Similarly, Z2 into Z2 conjugate is mod Z2 square, which is actually 4. So 4 by Z2 will become Z2 conjugate. So this guy will become Z2 conjugate. Similarly, Z3 into Z3 conjugate is mod Z3 square, which is actually 9. So I can say Z3 conjugate is 9 by Z3. So this guy here will be Z3 conjugate, right? In other words, what you have written, let me put forth the sixth also. So in other words, what you have written is nothing but mod of Z1, Z2, Z3, mod of this guy is Z3 conjugate, this guy is Z2 conjugate, this guy is Z1 conjugate, right? And we can also club all the conjugates under one roof and write it like this, correct? And this I can again break it up as Z1 conjugate, Z2 conjugate, Z3 conjugate, correct? Now, you all know the conjugate property that this will be same as mod of Z1 plus Z2 plus Z3, right? The property where I said modulus of a complex number and its conjugate are same because they're equidistant from the origin. So modulus of Z1 plus Z2 plus Z3 will be same as the modulus of its conjugate. So I'm replacing this guy with this. Okay. And this is something which we already know, 1, 2, 3. On the other side, we have a 6. So you can cancel off the 6 here and 6 here, only 1 will remain. So your answer for this is going to be 1. And that is what was expected out of you. So this is going to be a 1. Is this fine? Any questions here? Any questions, any concerns? Do let me know. Okay, Adrija, Shashwat, you got your mistakes? Okay, let's have few more problems before we switch on to division. Actually, we started this process to explain division, but somehow I think I should give you more practice on conjugates because you're going to need it. So we'll take a few questions on conjugates and then we'll move on to any other concept. Okay, so yeah, I mean, very simple question. Which of them is a wrong statement? Which of them is a wrong statement? I'm putting the poll on. Very easy. You should answer within 20 seconds, guys. 20 seconds, not even more than 20 seconds. Which of the statement is wrong? Good, good, good. People are on the right track. We'll stop in exactly 1 minute. Jaldi jaldi karo. Bega bega. 5, 4, 3, 2, 1, go. Okay. Most of you have gone for, stop the poll and then you'll say, most of you have gone for D for Delhi. That's absolutely correct. See, as you can see here, the first is the property which I had given to you. So this is a correct statement, hence it cannot be your option. Now here, this is nothing but mod Z1 into mod Z2 conjugate, and Z2 conjugate mod is same as Z2 mod. Both are same. So this is also a correct statement and hence not the right option because they're asking you for the wrong option. This is anyways a property, so this is also correct, hence not the right option. This is not correct. So there is no such link like Z2 and this. Ideally, they should have written Z2 here, but no link like that. So this is your right answer because it is the wrong statement. Okay. Okay, let's take this one. The complex numbers sin x plus I cos 2x and cos x minus I sin 2x are conjugates of each other for what values of x? For what values of x are these two conjugates of each other? Oh, sorry, I didn't run the poll. My bad. Relaunch the poll. Poll is on. Very good, very good. Guys, we are going to stop it in another 30 seconds. Very good, Shashwat. Come on, fast, fast. Jaldi karo. Guys, it's I always keep a timeline to a question because that's how you should also practice. The reason why most of you are slow in the exam, you are not able to attempt optimal number of questions is because you are not practicing in a time bound manner. When DPPs are given to you, you are taking like 5 days to complete it because you have to submit it on the 6th day or the 7th day. No. 15 questions, 1 hour, not more than that. So 30 questions, 2 hours, not more than that. So that 2 hours, your DPP should be over. After that, you look at the solution and try to understand where you went wrong. So that is the analysis phase. But solution phase is the time bound. Should not happen that you're sitting with a question for 2 hours or multiple hours to solve it. All right. Let me start the countdown. 5, 4, 3, 2, 1, go. Okay, let's stop the poll. Most of you have went with option number B. B for Bengaluru. Let's check. See, you're claiming that this is conjugate of this. That means sin x plus I cos 2x is conjugate of this guy. Now, conjugate of this guy means cos x plus I sin 2x. Okay. What does it mean? It means the real part is equal to the real and the imaginary part is equal to the imaginary. That means sin x is equal to cos x. Correct? So tan x is 1. Guys, it is lagging very badly. Let me switch off my camera for the timing. Yeah. For tan x is 1 means x is equal to n pi plus pi by 4. Remember the general solution that we had done in our equations? Okay. Ayyo Pranav. Conjugate, yeah. Conjugate of this, won't it be plus? Okay. And sin 2x is equal to cos 2x. That means tan 2x is equal to 1. That means 2x is equal to n pi plus pi by 4 means x is equal to n pi by 2 plus pi by 8. Now I don't think so The common solution of this will be n pi, because it cannot be n pi, because no complex n pi cannot be written as n pi plus pi by 4. So not possible. Neither can it be written by like this. Neither 0 is a common root. Even if I take some value of n, I will not get 0. So answer is option number D. No such value of x exists. Is that clear? Any questions, any concerns? Can we move on? So option D is the right option. No value of x. No value of x in this case is present. Okay. Is this fine? Next. Right. If z is x plus iy, where x and y are integers, find the area of the rectangle whose vertices are the roots of this equation. Let's have the poll on. So z, you put it as x plus iy. And the given equation is z into z conjugate cube is z conjugate z cube equal to 350. IIT JEE 2009 question. Not whole cube, Madhav. It is just the cube on the respective numbers. So read it like this. Yeah. Good, good, good. Somebody has given the answer. Last 1 minute. 2 minutes already over. Just 2 responses so far. All right, the countdown begins. 5, 4, 3, 2, 1, go. Okay. All right, end of poll. Most of you have gone with option C. C for Chennai. Let's discuss this. See, first of all, z conjugate cube and z conjugate z cube equal to 350. Before putting the values of z as x plus iy, I would like to take z conjugate common. So this will be z conjugate square z square equal to 350. Okay. Z conjugate is nothing but mod z square. Mod z square means x square plus y square. Correct. This guy is what? This guy is mod z square. Correct. And this is what? See, this is x square minus y square minus I to xy. And this is x square plus y square. Sorry, x square minus y square plus I to xy. Don't ask me how. You can just square x plus iy and just square x minus iy. This will be cancelled off. Okay. So what I will get is 2 times x square plus y square times x square minus y square is equal to 350. Drop this 2 factor. This will become 175. Now guys, this is a Diophantine equation. Okay. So x and y are integers. So this is also an integer. This is also an integer. Correct. So how can I break 175 as a product of these two? What all we can do? So if I take 175 as 5 into 35, no, sorry, 5 into 20, how much? 5 into 35, right? Yeah. 5 into 35, that means this is 35 and this is 5. So you will end up getting 2x square is 40, x square is 20. Nah, this will not work because x has to be integer. This combination will not work. Can I take 7 into 25? So let me try this one out. This is 25 and this is 7. So when you add it, yeah, this seems to work. This seems to work. I get x square as a perfect square, which is equal to 16. So x could be plus minus 4. And y square is equal to 18. Sorry, y square is 2y square is equal to 18. So y square is equal to 9. So y is equal to plus minus 3. Yes, this gives me integer values. Okay. So basically I get 4 answers from here. Your x comma y combination could be the following. It could be 4, 3. It could be minus 4, 3. It could be 4 minus 3. It could be minus 4 minus 3. Now the question setter is saying that if you make a Argand diagram out of these 4 points, so 4 comma 3 will be here, minus 4 comma 3 will be here, 4 comma 3 minus 4 comma 3, and 4 comma minus 3 will be here, and minus 4 minus 3 will be here. So if I connect it by a rectangle, let me do that. Tuck, 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 tuck. Sir, your rectangle is so bad, sir. I know. So what is the area of this rectangle? So this is 8, this is 6. Answer is 48 square units. Which option? Which option? Which option? Option number A. Guys, this is what JEE is demanding from you. Think laterally, think fast. Yes. Is it fine? So I think this is only prime factorizable as 5 square into 7. So you don't have much options to look at, right? You can either look at 7 and 25 or you can look at 5 and 35. Okay. You could also look at 1 and 175. That is another way. So I think only this is the possible case which will help us to find the answer. Is it okay? Can we move on to the next? Sir, could you move to the right? Okay. Done. Okay, let's move on to the next question. Let me check if I've taken some snapshots. This we have taken, this we have taken, this we have taken. Yeah, I think mostly we have done these questions. Yeah, let's do this one. Z and W are two non-zero complex numbers such that modulus of ZW is 1 and argument Z minus argument W is pi by 2. Then which of the following is Z conjugate W? Option is on. Sorry, poll is on. Very easy question, guys. Very easy question. You just have to apply your conjugate properties. Matter of half a minute, not more than that. But still, I'm giving you 2 minutes. Sir, आप कितने दयालु हैं, sir? You are giving us 2 minutes for a half-minute question. Good. One of you have responded. Good, good, good. I can see diversity in the answer now. Diversity is good when it comes to population, but not in the options. Lot of diversity coming in. Okay, 5, 4, 3, 2, 1. Do. All of you please vote. I'm going to stop it now. So half the Janta has voted, and in the half Janta vote, maximum of you have voted for option C. C for Chennai. Okay, let's check. See guys, what we need Z conjugate W, right? In order to know a complex number, you need two things about it. Modulus, argument. Okay, correct. So if somebody tells me the modulus and if somebody tells me the argument, my job is done, correct? Okay. So how do I get R? R is nothing but modulus of this guy. Thankfully, we can write it like this, and thankfully we can write it like this, and thankfully we can write it like this also, which is 1, which is as per the given question 1. Okay, so R is 1. Okay, so all the options are modulus 1. Ayyo. Okay, I'll have to go one step further. What is argument of Z conjugate W? As per our multiplication rule, we know it's argument of Z conjugate plus argument of W. Correct? Remember, I told you argument of Z1 into Z2 is argument of Z1 plus argument of Z2. And argument of Z conjugate is negative argument Z. Remember, modulus conjugate properties. Okay. I can see this term is negative of whatever I need, right? So if I take a negative over here, isn't it given to us in the question? Yeah, this is given to us in the question. So answer is minus pi by 2. Correct. So this guy is minus pi by 2. So your answer will be 1 e to the power minus I pi by 2, or in a more sober sense, or more you can say polar sense, it is 1 cos minus pi by 2 plus I sine minus pi by 2, which we all know is negative I. Option number D is correct. D for Delhi. Janta went for Chennai, I guess. Chennai, only 2 people went for Delhi. E baba, ki ho cheese. Ki gondogol. I think only Adrija can understand what I said. I said, what's happening? Oh, and Aritra also. Okay. So you don't have to take any other route. It's just a straightforward route. For any complex number, you need its modulus, you need its argument. All the information is given to you in the question and you can easily solve it. Can I go on to the next? Can I go on to the next question? All right. Next is the thing that we wanted to learn, division. Right? This was what we actually wanted to learn. Okay. Now, division of two complex numbers Z1 by Z2. So if you write these complex numbers in, let's say, point form, if you write it in the point form, where is I gone? Yeah. So A1 plus IB1 and A2 plus IB2, if you write it as a point form, then normally we are asked in our school exams to write this answer as C plus ID form. So how do I convert it? Here we will need our conjugate help. So what I'm going to do is I'm going to multiply the numerator and denominator with the conjugate of the denominator. Why am I doing this? This will help us to realize the denominator. Don't use the word rationalize. You're not rationalizing it. There's nothing rational, irrational about it. You are realizing it. Not that English realization. Oh, I realized it, sir, now. not that realization. You are making it real. That is realization, right? So when you do that, your denominator will actually become A2 square plus B2 square. And on the numerator, you get A1, A2. So let me write down the real parts first. A1, A2. And you'll have minus I square B1, B2, which is plus B1, B2. Okay. And if you take a I common, you'll have A2, B1, A2, B1 minus A1, B2. Got it? Now again, this is your C and this is your D, right? This is a super dry form. No information whatsoever is extracted from this. This is just a waste effort. Okay. Why am I teaching you if it is a waste thing? Probably you may require it in school. Okay. Right. This doesn't give you any insight. What is happening to Z1 by Z2? Where is it located? Right. What operations are happening between the moduli of Z1 and Z2? What operation is happening between the arguments of Z1 and Z2? No information is known from it. Just a waste form. Okay. So what I'll do is I'll do the same activity when I'm representing the complex number in the polar form. This was when it was in the point form. So I'll write it the same thing in the polar form. I think that should give us a better insight as to what is happening. So in polar form, if you write those complex numbers, so let's say I write Z1 by Z2 as R1 cos theta 1 plus I sin theta 1 by R2 cos theta 2 plus I sin theta 2. So this one will be R1 by R2. Now see, the same thing that you are going to do, that you had done with your point form, you are going to do here also. So no difference in the approach, but yes, the outcome will be more insightful. So I'm going to multiply with the conjugate of this guy. So this guy's conjugate is this. Okay. So let's multiply both numerator and denominator. Okay. Now, in the denominator, you are going to get cos square theta 2 sin square theta 2. That's a big one, right? Pythagorean identity, cos square theta plus sin square theta. On the numerator, you will get cos theta 1 cos theta 2, okay, and plus sin theta 1 sin theta 2, plus sin theta 1 sin theta 2. So this is the real part. Imaginary part, I will write it in yellow. So you'll have sin theta 1 cos theta 2 minus cos theta 1 sin theta 2. Okay. And if you see these two terms carefully, they will take you to your childhood days when you learn trigonometry. Remember when you were very small, we learned that this was cos theta 1 minus theta 2. Right, Madhav? Which class you were in? LKG or UKG? Right? So what do you observe over here? We observe here that we end up getting an answer whose modulus is this guy and whose argument is this guy or this guy, whatever you want to call it. Okay. So if you treat this as if you have written r cos phi plus I sin phi, then you can claim that your r is nothing but r1 by r2. So your r, which is your modulus of this answer. See, z1 by z2 gives you a complex number only, right? That complex number modulus is your capital R, and that is nothing but R1 by R2, and that is nothing but mod Z1 by mod Z2. A good information for us. So what we now understand is that when you are dividing one complex by the other, you get an answer. You get an answer whose modulus is the ratio of the moduli of Z1 and Z2. Right? One thing is clear from here. Second thing that is clear from here is your argument of Z1 by Z2 is nothing but theta 1 minus theta 2, which is nothing but argument of Z1 minus argument of Z2. Right? Just like in addition, just like in multiplication, they got added up. In division, they got subtracted up. You'll say, sir, it is very much like the log properties. Yes, it is very much like the log properties. And please note that if they asked you for the principal argument, don't forget to adjust this answer between minus pi to pi, minus pi exclusive. Okay. So thanks to this polar form that now we'll be able to figure out on the Argand plane, where does Z1 by Z2 lie. Now the same thing can be done in a very quick form had you written the Euler notation for it. So if you write it in the Euler form or the exponential form, if let's say Z1 is R1 e to the power I theta 1 and Z2 is R e to the power I theta 2, you can directly see that R1 by R2 will become the modulus of the quotient and theta 1 minus theta 2 will become the argument of the quotient, or Z1 by Z2. That's what we call as quotient. Yeah. Is this fine? Now where is Z1 by Z2 located? How do we figure it out? Let's try to see it. So let's say this is my real Z axis. This is my imaginary Z axis. So let's say Z1 is located over here. Let's say at a distance of R1 from the origin, or you can say the pole. Okay. And let's say this angle is theta 1. And Z2 is located somewhere over here at a distance of R2 from the origin and at an angle of theta 2. Okay. So now where is Z1 by Z2 located? So how do we figure it out? Now see what is happening over here. Try to understand. Try to understand. When I was discussing this, I wanted you to have a geometrical picture in your mind. So what are you doing with Z1? You are first rotating it clockwise by an angle of theta 2. Because your argument of Z1 by Z2 got reduced by theta 2, right? It became theta 1 minus theta 2. So just like in multiplication, you were rotating anti-clockwise by theta 2. In division, you will be rotating it clockwise by theta 2. That is the first difference. Second thing is, the modulus in case of multiplication got factored by R2. In this case, it will get divided by R2. R2 is the modulus of Z2. Are you understanding what is happening? So you are rotating it clockwise and reducing it by R2 factor. Now, whether it is reducing or increasing, that depends on R2. I can't comment that it is always reduction. What if R2 is a fraction? If R2 is a fraction, it will increase. Okay. Right? So it is factored by, you can say 1 by R2. That would be a better word to use. Are you getting that picture in your mind? Rotating clockwise and factoring the modulus by 1 by R2. Got the point? Okay. So in light of this, if I have to locate my Z1 by Z2, what I will do is from this line O, let me name it. From this line OA, I will rotate theta 2 angle. So let me use a blue color. Theta 2 angle I will rotate. So this guy is theta 2. Okay. And this length, let me write it in blue only. This length will become R1 by R. Where is R1? R1 by R2. So this guy will be your Z1 by Z2. Understood? Are you getting a picture? Correct. Now, somebody figured out, of course, authors and mathematicians figured out, somebody figured out that this triangle, sir, what is wrong with your drawing? Somebody figured out that triangle OBP and triangle, let me call it point C. So somebody figured out that triangle OBP is similar to triangle OAC. Is that correct? Let's see. First thing is, yes, this is theta 2. This is also theta 2. Check point 1. Second thing is, let's say if I take OB by OP. Okay. OB by OP will be what? OB is R2. OP now. What is OP? OP I didn't tell you. Sorry, my bad. P was at 1, 0. So OP is 1. It's same as OA by OC. Let's check. OA is R1, correct? And OC is R1 by R2. R1 by R2. So R2 will go up, okay, and it will make it this. Yes, they are same. So we can directly say these two triangles are similar. Okay, so these are certain things which we need to keep in mind when we are imagining the division of two complex numbers. So I have a question. Sir, what is P? P is 1, 0, Aditya. Sorry for not writing it earlier. Is that fine? Any questions, any concerns? Okay, let's take questions. Let's take questions on divisions. Can I go on to the next slide? If everybody has copied, can I move on to the next slide? All right. We have done almost a lot of questions. काम करते हैं. We will do. We will do. We will do. We will do. Not really division. Not really division. Okay, let's try doing this question. Yeah. W is alpha plus I beta. Beta is not 0. Z is not 1. Satisfying this condition, W plus W conjugate Z by 1 minus Z is purely real. Find the values of Z. Then the set of value of Z is. I don't know whether it is directly related to what we are doing right now, but let's solve it. It looks very interesting to me. So let's attempt this question. JEE 2006 question. JEE 2006 question. Poll. Let's have the poll. Good, good, good. Actually, this has to do more with conjugate thing that you learned. Last 1 minute for this. Last 20 seconds. 5, 4, 3, 2, 1. Go. All right. So very, very skewed response as of now. Please vote, please vote, please vote. Everybody is still voting. Okay. Most of you have went with option number B. Let's check. See guys, when you read this word purely real, at least I am reminded of that conjugate property, where I said that if a complex number is purely real, then Z will be equal to its conjugate. Correct? Yes or no? So what I'm going to do is, if this is purely real, I can say this guy is going to be equal to its conjugate. Big conjugate symbol, right? And you have also learned that conjugate property, that Z1 by Z2 quotient conjugate is the conjugate of the numerator and denominator separately. Correct? This is as good as W conjugate minus W conjugate. Conjugate is W, and 1 minus Z conjugate is like 1 minus only the conjugate on Z, because there's no point putting a conjugate on a purely real complex number, right? So let us cross multiply. Let's see if something cancels out. Let's cross multiply. This multiplies to this. This multiplies to this. Let's see what happens. So W minus W conjugate Z times 1 minus Z conjugate is is equal to this. Let's expand this. So WZ conjugate minus W conjugate Z plus W conjugate mod Z square. Here also I'll have W conjugate minus W conjugate Z minus WZ conjugate and plus WZ conjugate square. Okay. Let us check if some terms get cancelled. I believe that this guy will get cancelled with this guy. This guy will get cancelled with this guy. Correct? And you will have W minus W conjugate and plus mod Z square W conjugate minus W is equal to 0, which is actually W minus W conjugate. You can write it like this. You can write it like this: W conjugate minus W times mod Z square minus 1 equal to 0. Correct? Now, there are two possibilities. There are two possibilities. Either W is equal to W conjugate or mod Z is equal to 1. But this is not possible, because if this is possible, then W must be a purely real complex number. If it is a purely real complex number, that means beta should have been 0, but they have given beta is not 0. That means this possibility is ruled out. This possibility is ruled out. That means only possibility is mod Z is equal to 1. correct? So mod z equal to 1 is the only possibility, and at the same time they have given z is not equal to 1, so that is fine. So both the options, both these conditions are satisfied by option number B. That's what we can comment. Option B is the right option. Let's see what was the response of Janta. Janta was absolutely correct. B is absolutely correct. Okay. Sorry, this question had nothing to do with division. Let me give you one more. Let's take this one. If Z1 and Z2 are conjugate pairs, if Z1 and Z2 are conjugate pairs, and Z3 and Z4 are conjugate pairs. Okay. Simple question is, so let's do this. So argument of Z1 by Z2, sorry, argument of Z1 by Z4 plus argument of Z2 by Z3 is which of the following? Option A, pi. Option B, pi by 2. Option C, 0. Option D, none of the above. Z1, Z2 are conjugate pairs. Z3, Z4 are conjugate pairs. We have to find out, sorry for writing one A in small and one A in caps. Yeah. Find the argument Z1 by Z4 plus argument Z2 by Z3. Very good. I have got 5 responses so far. Very easy question, guys. You just have to apply one of the properties that we learned while we were discussing division of complex numbers. Z1, Z2 are conjugate pairs. Z3, Z4 are conjugate pairs. Don't forget that. Last 20 seconds. Five, 4, 3, 2, 1, go. All right, so just 14 of you, half the class has responded so far. Most of you have gone with Chennai, option number C. Okay, now let's see. See, we have already discussed that when you're dividing one complex by the other and you're taking the argument, just like your log properties, you can write it like this. Correct? Similarly, this can be written as argument Z2 minus argument Z3. Okay. Let's not forget that Z1 and Z2 are conjugate pairs. So argument Z1 is negative of argument Z2. Right? Similarly, argument Z3 is negative of, let me remove my camera from here, is negative of argument of Z4. Okay. That is to say that argument of Z1 plus argument of Z2 is equal to 0. And argument of Z3 plus argument of Z4 is also equal to 0. So this plus this, that is going to be 0. And in this case also, if you take a minus sign common, this will also become a 0. So ultimately your answer is going to be a 0, which is option number C. Janta is absolutely correct. Okay. So you don't need to assume anything for you to do it. You can directly apply basic properties and get this problem solved. Is this fine? Is this clear? Is this understandable? Okay. Now let's talk about another operation, which is finding the nth power of a complex number. Okay. So the next operation that we are trying to look at is finding the nth power of complex numbers. Complex numbers. Okay. So if you have a complex number, okay, let's say, and I want to find out the nth power of it. Of course, here n could be two things. It could be a whole number, or a positive integer, or a negative integer, or it could be a fraction. Okay, so let us try to look into both the scenarios when we are trying to learn this concept. So this n, it could be two cases for us. It could be either a, let me write it like this. It could be either a integer, or it could be not an integer, or you can say it's a rational number, p by q form. Okay, so it could be a rational number of p by q form. Of course, q should not be 0. Okay, and let's try to look into this scenario. Let us try to look into this scenario. So first of all, let's take the case where n is an integer. So first case, I'll take n as an integer. Okay. Now if n is an integer, the best way to look at z to the power n will be, let us say z is r e to the power I theta. Okay. And if you raise it to the power of n, you would realize that you are actually doing this activity. Correct? So your r will get raised to the same power n, and your e to the power I theta, the power will get multiplied to n. Correct? So isn't it like saying you have actually done this? So when you are multiplying a complex number, sorry, when you are raising a complex number to the power of n, you are raising the same power on its modulus, but you are multiplying its argument by n. Again, very much like the log properties. Very much like the log properties, isn't it? So thanks to the Euler form that we are able to figure this out very, very easily. Yes, this exponential form makes our life so easy. Correct? And even though we are using an Euler form, this was first figured out by a French mathematician whose name was De Moivre. De Moivre. So this is called the De Moivre's theorem. The pronunciation is not Moivre, it is Moivre. De Moivre's theorem. Some of you would have learned French in your school. Okay. So when you're raising a complex number to an integral power, this is what you can actually write for the answer. Is this fine? Guys, few things to be noted down over here. Number one, important pointers. Number one, you only get one answer for it. Okay. So only one answer is obtained when you are raising the complex number to an integer power. When n is an integer, only one answer is obtained. Okay. Unlike the case of when you are raising it to a fractional power, or you can say a rational number of p by q form, which we'll talk in some time, not right now. Second thing is, many people get confused by these two imposters. If your complex number has been written in this form, sine theta plus I cos theta, and let's say if you're raising this to a power of n, be careful of this. It is not equal to r to the power n sine n theta plus I cos n theta. This is one of the biggest imposters, or you can say fraud expression that may deceive you. Do not make such a mistake. Second mistake is, if you have your complex number written in this form, okay, where theta and phi are not the same. Okay, sometimes somebody can write a complex number in this way to deceive you, right? Then this also cannot be written in this form. Sorry. Are you getting my point? Do not make these mistakes. Very, very common mistakes. Please be careful of this. Be careful. Okay. Yes. However, if you have something like this, r cos theta minus I sin theta, and somebody is raising it to a power of n, then you can write it as r to the power n cos n theta minus I sin n theta. That is not an issue. This is fine. This is perfectly acceptable. Is this fine? Now, why it is acceptable? Very simple. See, if you're raising it to the power of, if you're putting a minus sign over here, this itself is saying you're doing cos theta minus theta plus I sin minus theta. Correct? Yes or no? Yes or no? So this itself is like saying r cos theta plus I sin theta whole raised to the power minus 1, and then again whole raised to the power this. Okay. So if you take the minus outside, if you just take the minus outside, for example, if I break it up like this, r to the power n and cos theta plus I sin theta to the power of minus n, then again by de Moivre's theorem, you can bring this minus n inside and it will become cos minus n theta sin minus n theta, which is back to r to the power n cos n theta minus I sin n theta. So the same expression is what we end up getting. Okay, so you can directly skip all those, you can say indirect roots and directly jump to the business. Okay, so this can also be written like this. Is this clear first of all? So the de Moivre's theorem, when n is an integer, whether positive, negative doesn't matter. Whether positive, negative, integer doesn't matter. This rule will always work. Is this clear to you? Is this clear to you? Sorry, I missed out an n over here. Okay, so this rule is very, very important. Okay, so before going on to the fractional part, I will like to take up a question on this. I hope you have noted this down. Anybody wants me to drag the screen down, up? Yeah, I'm not going anywhere, Akash. I know you want to copy a lot of things. Yeah. Further down, or is it fine? Further down. Okay. I'll give you a break. Just let me take some questions on this. Just one question. Express this as a plus ib form. Indirectly, they are saying mention the value of a and b. Ayyo, Akash. Okay, let us do this question and then I'll go back. What I'll do, I'll give you a break and I'll leave the screen on that. Okay, Akash, is that fine with you? Sorry for the inconvenience, but let's do this problem and then go back. De Moivre's theorem is very important, so please take it very, very seriously. Yes, anybody with the value of A and B? Nobody. Is it so difficult? Okay, numerator term, if you see, that is perfectly in the form. Let me do work with the denominator a bit, because denominator is slightly uh, in a different form. Okay, so let's say sine theta plus I cos theta to the power of 5. Let me again remind you, this is that one of the imposter forms, fraud forms. Okay, don't fall for it. Okay, don't put sine 5 theta plus I cos 5 theta. So the better way to would be just take a I common in the denominator, in the bracket terms. So it will be cos theta and it will be minus I sin theta. Correct? So this you can write it as I to the power 5, and this is cos theta minus I sin theta. Now guys, let me just write one more thing over here. I to the power 5 is I, and cos theta plus I sin theta is cos theta plus I sin theta to the power of minus 1, which will multiply to this and give you a minus 5. Okay, so the denominator you can safely take it to be this. Now finally your term, that term that you have is nothing but cos theta plus I sin theta to the power of 4 by I, 1 by, now 1 by I is like minus I. Cos theta plus I sin theta to the power minus 5. Okay, so this will become minus I cos theta plus I sin theta to the power of 9. So this will give you minus I cos 9 theta plus I sin 9 theta. Now you can multiply your minus I with it. So this will give you sin 9 theta minus I cos 9 theta. So this is your A and this is your B. Oh, sorry, 9 theta. Is that fine? Any questions? Any questions? Any concerns? Clear? Very good, Aditya. Aditya got it. Ah, Aditya, I think you messed up your cos and sine. Is that okay? All right. So we'll pause here. So the next thing that we are going to talk about under the De Moivre's theorem is when your n is a rational number p by q form. Okay, of course p and q are integers here and they have been expressed in the simplest form. So n p by q has been expressed in the simplest form, means there is no common factor between p and q. That means they are relatively prime to each other. Okay, so now first of all let us try to understand this. When you raise a complex number to the power of p by q, how many answers should you get from here? How many answers should come out from this? Yes, any response? If I raise any complex number to the power of q, how many answers should come out from here? In the previous case, we only got one answer, right? In this case, does anybody know how many answers will come out from this? Okay, now I think you'll know it in a better way if I write it like this. Now, does it ring a bell? Okay, I'll tell you. So this will give you Q answers. Okay, and those Q answers are basically called as the qth roots of z to the power p. Okay, so under this particular discussion, we are going to learn how to find these Q answers. Not one, not two, but Q. For example, let's say if you're raising it to the power of 3 by 4, then you'll get 4 answers out of it. If you're raising it to the power of 1 by 5, then 5 answers will come out of it. So how to get those 5 answers? Let us try to understand that. Now, taking a clue from this, if let's say if your complex number was r cos theta plus I sin theta, and if you raise it to a power of p by q, as we had mentioned that we can actually write it like this. So it will be r cos theta plus I sin theta whole raised to the power of p, and then whole thing raised to a power of q. Sorry, 1 by q, not q, 1 by q. Okay. Then at least in the inside part, that is here, I can apply the first part of the De Moivre's theorem, which I discussed with you. So I can write it as r to the power p cos p theta plus I sin p theta. Correct? And let's write down to the power of 1 by q. Now, can I now do 1 by q into this? If I do that, I'll only get one answer. But that is not the case. I have to have q answers coming out of it. So what did De Moivre do? He said that we can write this term cos p theta as cos 2k pi plus p theta, and we can again write I sin p theta as I sin 2k pi plus p theta without affecting anything. Was he correct? Yes, he was correct, because cos and sin both are periodic with a period of 2 pi. Okay, k is some integer here. What is that integer? I'll tell you in some time. Okay, so he said that write cos p theta as cos 2k pi plus p theta, because it will still remain the same. Both of them are same expressions. And write sin p theta as sin 2k pi plus theta. So these two are also the same expressions. Okay. Then he said, let us introduce this 1 by q inside in this way. So just like we had done for the first case of De Moivre's theorem, multiply with 1 by q. So this will give you this. Correct? Now, in order to get q different answers, he said that put k as q consecutive integers. Any q consecutive integers. Any q consecutive integers. Okay, but we normally preferably we put q, but preferably we put k as 0, 1, 2 all the way till q minus 1. Okay, but in reality you can put any q consecutive integers. Okay, so let me demonstrate it with a simple example. Simple example. Now, if your question comes, why not more than this? It is because he realized that if you put more than this, let's say if you put q, you will come back to the same root as what you obtained for 0. If you go to q plus 1, you will come to the same root as what you obtained for 1. So there will be repetitions of the same set of roots over and over again. Okay. So why any n consecutive? It is because if you choose any multiple of it, you will get back to the same root. We'll see. Let us take an example for it first. Let's take a simple example for this. Have you all copied this down? Could you go up for a second? At this point, Madhav? No, my above. It is not any integer. Your k is any q consecutive integers. Preferably, you can write it as 0, 1, 2, 3, 4 till q minus 1. Let me give an example. You'll understand from that example. Okay. So let's take a question. Let's say I have a complex number 1 plus I. I'll take a simpler case. Okay. I'm raising it to the power of, let us say, let's say 2 by 5. So I want to raise it to the power of 2 by 5. Okay. So how many answers should come from here? So I will get 5 answers from here, right? Or I'll get 5 roots from here, so as to say. Okay. So what are these 5 answers? Let's try to figure it out. So first of all, write 1 plus I in the form of polar form. So we know that this in the polar form can be written as root 2 cos pi by 4 plus I sin pi by 4. Correct? Now when you're raising it to the power of 2 by 5, treat as if you're doing this first and raising it to the power of 1 by 5. Okay. So root 2 cos pi by 4 plus I sin pi by 4 whole raised to the power 2 and then whole thing raised to the power of 1 by 5. Right? Now, this power of 2, you can easily write it as 2 cos. Now this 2 will come and multiply here. So pi by 2 plus I sin pi by 2. Okay. Whole raised to the power of 1 by 5. Now remember the step which I told you. So De Moivre said you can write cos pi by 2 as cos 2k pi plus pi by 2 plus I sin 2k pi plus pi by 2. Okay. Whole raised to the power 1 by 5. Now introduce this 1 by 5. So it will be 2 to the power 1 by 5. Now here you have to take the real value of this. Okay. And this will be cos 1 by 5 multiplies. So this will give you 2 pi by k by 5 plus pi by 10 plus I sin 2k pi by 5 plus pi by 10. Okay. And then he said, start putting k value as any 5 consecutive integers. So we'll choose k value as 0, 1, 2, 3, 4 for convenience. And this is the most preferred value because it is going to give you simple results. If you want, you can choose 100, 101, 102, 103, 104 also. But again, you will have a problem in calculating it. Okay. So this is preferably. Again, I'm repeating preferably. Okay. It's not an urgency. Now, and I'll show you if you put on the next value 5, what will happen. So if you put k equal to 0, what do you get? You get 2 to the power 1/5. You will get cos pi by 10 plus I sin pi by 10. Okay. If you put k as 1, what do you get? Now, when you put k as 1, you get cos 2 pi by 5 plus pi by 10 plus I sin 2 pi by 5 plus pi by 10. Okay. For the purpose of simplicity, can we write this as this e to the power I pi by 10 in Euler's form or the exponential form? Acha, one more thing I would like to highlight. Right now, I am basically not restricting my angle to minus pi by pi. So if I exceed minus pi by pi, that is fine. I mean, I'm not restricting it to minus pi by pi, minus pi to pi as we do it for the principal argument. So please consider that I may exceed that given interval. Okay. But that is not going to affect my answer. Don't worry about it. So if you put k as 2, directly if I write it down, I'll get 2 to the power 1/5 e to the power I 4 pi by 5 plus pi by 10. If I put k equal to 3, I get 2 to the power 1/5 e to the power I 6 pi by 5 plus pi by 10. And if I put k as 4, I'll get is this fine? Okay. Now, what is important for us is to know its position on the Argand plane. So these are your 5 answers: 1, 2, 3, 4, 5. Let us position it on the Argand plane and we learn a pattern there also. So first, everybody please copy this down. Done? Okay. So one thing that you would observe over here is that all these roots, all these 5 roots, let me call them as Z1, Z2, Z3, Z4 and Z5. All these 5 answers, they're having the same modulus. That means they all are located at the same distance from the origin. Correct? Yes or no? Yes or no? Right? So can I say one thing, that they are located, all of them are located at, let's say this number was r e to the power I theta, then all of them are located at, and let's say this power was p by q. Can I say all of them are located at r to the power of p by q distance away from the origin? So I'm trying to just observe what is happening from these answers. So my first observation is these roots are located at a distance of r to the power of p by q, r being the modulus of the given complex number whose power you are trying to find out. Okay, and p by q is the given power itself. Okay. Second thing you'll observe that the first argument that you see, pi by 10, it is actually p by q theta. So see, what was the argument of this? Pi by 4, right? So 2 by 5 into pi by 4 will give you pi by 10. So this is your p by q theta, right? Yes or no? And then the second argument that you see here, it is actually 2 pi by q plus p q by p by q theta. That means in the previous argument, you made an increment of 2 pi by q. So p will not feature over here, only q will feature. Okay. And for the subsequent arguments, you kept on increasing it by the same value. That means this is now 2 pi by q plus 2 pi by q plus p theta by q. That means there is a constant increment that you are making of 2 pi by q in your answer in the previous argument, right? This is a very, very important observation that will help you to find out your answers sometime even without undergoing the same process. If you make this observation, you can get your answer pretty quickly. So let us go to the Argand plane first. Let us go to the Argand plane. See, if you see here what is happening, then the first root is located at a distance of r to the power p by q and at an angle of p theta by q. This angle is p theta by q, where r is nothing but the modulus of the given complex number whose power you are raising, right? So when you're raising z to the power p by q, right, this r is the modulus of this complex number. Okay. And the subsequent roots, let's say I call this as Z1 root. The subsequent root will be located again at the same distance, which is r to the power p by q. So let's say Z2 is located here. Again at the same distance of r to the power p by q. But now its argument would be more than the argument of the previous by 2 pi by q. So there is an increment. You can say you are rotating it anti-clockwise further by 2 pi by q. Okay, and keep on doing the same thing with the all the roots. So the next complex number or the next root will be Z3, which will be again located at a distance of r to the power p by q. And again, this additional angle over here will be 2 pi by q. Are you getting my point? Like that, you can start finding all your roots. Okay, dot, dot, dot. I'm not writing everything. Okay, this will be Z4, this will be Z5, dot, dot, dot. Are you getting this point? So if you observe this, you can find out all your Q answers without applying De Moivre's theorem at all, because this is derived from the De Moivre's theorem. And a serious JEE aspirant will never waste time, doing all this entire process. He'll immediately start doing this. Okay, your answers can come in less than 1/3 the time when you observe this pattern. Are you getting my point? Second thing that you will observe over here is that if, let's say, you connect all the roots over here, let's say if I join all the roots, you will end up getting a Q-sided regular polygon. I'm not completing it because I don't know what the value of Q over here. So this will be a Q-sided regular polygon. Okay. So a question may arise in your exam that if, let's say, I find out the roots of this particular complex number and arrange them on the Argand plane and connect those roots by, let's say, straight lines or line segments, and I get a polygon, what could be the side length of the polygon? What could be the area of the polygon? What could be the circumcircle radius of that polygon? What could be the incircle radius of the polygon? All those things can be asked to you. So be prepared for such kind of questions. Are you getting my point? Is this idea, is this observation clear? Okay. If this observation is clear, then we'll take up few special cases. One is the cube root of unity and other is the nth root of unity. And that's what is going to be very important for you. Clear, everybody? Gayatri? Clear, everyone? Okay. Would you like to take one more example? I am sure you want to take one more example. Okay, let's say, I'll take an example. Let's say I want you to find out, what should I take? What should I take? What should I take? Let's take I only. Okay. Let's say I want to find out I to the power of 2 by 3. I want to find I to the power of 2 by 3. Now see, I will not use any mathematical notation. I'll just do it from my Argand plane diagram. See how. So my R here, remember, 1 is nothing but, I is nothing but 1 e to the power I pi by 2. So that R which I'm talking about is actually 1 and the theta that I'm talking about is pi by 2. Now all of you see, I will have how many answers coming out from it? So this operation will give me how many answers? 3 answers, right? Absolutely. Let's see what are those 3 answers. I will not even write a single mathematical thing. I'll just keep on positioning the roots. So the first root that I will be putting will be located at a distance of 1 to the power 2 by 3 and at an angle of 2/3 of pi by 2. 2/3 of pi by 2 is pi by 3. So one angle is, one of the roots will be located over here. Okay. Okay. So where it is located? It is located at an angle of pi by 3 and at a distance of 1. So this will be one of your roots. Is it fine? Any questions? Okay. Second will be located at a distance of same, but the previous answer, that is 2/3 of pi by 2 incremented by 2 pi by q. Q is 3 over here, my dear. Please be aware. This is your Q. So this pi by 3, I will increase by 120 degrees. Now this is already at 60 degrees. Okay. So if I go 120 degree, I'll reach over here. So again, this will be located at a distance of 1 from here. Okay. So this will be your Z2. By the way, I will also write down the values here, or I will write it down a little later on. Okay. Then again, the next root will be 1 to the power 2 by 3. And further, there will be an increment. Further, there will be increment of 2 pi by 3. Okay. So next root will come over here. So let's say this is Z3. And again, this is at a distance of 1 only. Got it? Yes or no? Okay. And if you connect these three roots, you will actually end up getting an equilateral triangle. Doesn't look like in my diagram, but yes, it is an equilateral triangle. So this will be giving you an equilateral triangle. A three-sided regular polygon. What is a three-sided regular polygon? Obviously an equilateral triangle. Correct? Are you getting my point? Okay. Let's figure out what are these Z1, Z2, Z3, etc. Z1 will be 1 to the power 2 by 3 cos pi by 3 plus I sin pi by 3. Okay. Z2 will be 1 to the power 2 by 3, which is actually 1. There is no point writing 1 to the power 2 by 3. It sounds so stupid to write it like that. And cos, yeah, this will be pi by 3 plus 2 pi by 3, which is pi, which is cos pi plus I sin pi. Actually, it is minus 1, to be more frank. Okay. And Z3 will be 1 cos. Now remember, here I have exceeded my principal argument range. But functionally, it is not going to make a difference. Functionally, it is not going to make any difference. Okay. So let me write it down. This is 4 pi by 3 plus pi by 3. 4 pi by 3 plus pi by 3 is 5 pi by 3. Okay. And if you are further interested in knowing its point form notation, this is going to be half plus I root 3 by 2. Okay. This is of course minus 1. I have already written it over here. And this is going to be half minus I root 3 by 2. Is this fine? Any questions? Right? So if I know the pattern, I don't have to follow the regular approach of your de Moivre's theorem. Okay. Now further question can come, hey, what's the side length of this equilateral triangle? You'll say root 3 because this length is going to be root 3. Okay. What's the area of this equilateral triangle? Area will be root 3 by 4 into a square, which is 3. So this will be your area. Okay. Any type of question can be framed. Okay. Any type of question can be framed. They can ask you the circumcircle radius. They can ask you the incircle radius. Okay. By the way, you should know all your properties of triangles. Day before yesterday, I was doing it with your seniors. They had all forgotten. Is this fine? So let me take an opportunity to take something very interesting over here, which is cube root of unity. Cube roots of unity. So the number 1, what is the cube root of it? This is what we are trying to find out. Up till now, you knew only one of the answers, which was 1. Cube root of 1. Most of you will say 1. But 2 more answers are there, which you were not aware of till this stage. Now you will be able to find that out. So let's figure it out. Can I write 1 as a complex number as 1 e to the power I0? That means the r for this is 1 and theta for this is 0. Correct? I will follow my pattern approach. I will not apply the de Moivre's theorem again and again. So my first root, so 3 answers will come out. The first root will be located at a distance of 1 to the power 1/3 and at an angle of p by q times 0. That is 0 only. So at a distance of 1 and at an angle of 0. So this will be your very first root. And you'll be happy to know that this is your one answer. The answer is 1 in this case. This is the only answer which you actually knew. What are the other 2? Let's figure it out. So next will be located at a distance of 1 to the power 1/3 and just add 2 pi by q. Q here is again 3. So add a 2 pi by 3 to the answer. So we'll reach over here. So this is your Z2. So let me just connect it like this. This angle is 2 pi by 3. Got it? Okay. The third root will be again located at a distance of 1/3. So let me write it Z1, Z2, Z3. And you will further increase it by 2 pi by 3. So keep increasing by 2 pi by 3. That means 4 pi by 3. So 4 pi by 3 will be full this way. Okay. So this will be again 2 pi by 3. This is your Z3. By the way, Z2 will be minus half plus I root 3 by 2. And Z3 will be minus half minus I root 3 by 2. Please make a note of this. This complex number is famously called omega. And this complex number is famously called omega square. Now, why it is called omega square? I'll discuss about that, but first note this down. Okay. And again, if you connect these roots, they will give you an equilateral triangle, same as what we obtained for the previous case also. Yes, any question? I can see one question arising. Sir, how it is 2 pi by 3? Aditya, I have to go back again to the previous slide. You have to increase your answer by 2 pi by q. Didn't we discuss that? You people don't note this down. Come back here. See, what did I write here? First angle, first root will be at an angle of p theta by q. Then you have to keep adding. You have to keep adding 2 pi by q, 2 pi by q, 2 pi by q, like that. So q is 3, no, in this case. Ayyo, don't note it wrong. Full gone then concept if you're noting things wrong. Ask in case of any doubt. Please ask 10 times, but don't copy anything wrong. Is this fine? Interesting, right? Okay. Okay. Now, one thing is, if you write them in the polar form or in the Euler form, this is actually 1 e to the power I0. This is actually 1 e to the power I 2 pi by 3. And this is actually 1 e to the power I 4 pi by 3. Now you can see, if you square this up, you will actually end up getting this number. That is why if this is omega, then this will be called omega square. Is this fine? Okay. So we'll take certain properties of this because this particularly is very important. We are going to come across the cube roots of unity several times. So there are some special, expressions that we are going to see very frequently. So let us look into the properties of cube root of unity. Yeah. Properties of cube root of unity. The first property that is needless to say, but still I'm saying, is if you raise omega to any power which is a multiple of n, which is a multiple of 3, sorry, which is a multiple of 3, okay, you will always get a 1. Why? Very obvious, because omega is a cube root of unity, so this is 1. So if I raise it to any power n, okay, you'll still get a 1. Is it fine? No problem with that. Okay. Second important thing that we'll learn from here is that omega and omega square, they are actually roots of z square plus z plus 1 equal to 0. Now you must be wondering how? How is this possible? How did I come up with this equation? That's very simple. All of you, let's go back. See, we were finding cube roots of 1, right? Let's say I call it as z. That means I'm saying indirectly z cube is equal to 1. That means I'm saying z cube minus 1 is equal to 0. If you factorize it, it becomes z minus 1, z square plus z plus 1 equal to 0, right? So I'll get one answer as 1 because of this factor, and I will get other 2 factors from here. Okay, so I'll get other 2 roots from here, which is actually your omega and omega square. So hence omega and omega square are actually roots of this equation. This is a very important piece of information for us, right? And therefore we can say one thing for sure, that omega square plus omega plus 1 will always be 0. Very important property, because omega is going to satisfy this equation. Even if you put omega square, you'll end up getting the same result, because you'll get omega square square, which is omega to the power 4, and omega to the power 4 is omega cube into omega, and omega cube is 1. So this will actually give you omega square. Let me write omega square in front, plus 1. This will still be 0. Okay, very important property. Is this fine? So please remember that now you can factorize. Now you can factorize an expression like this, which you were not able to factorize before. So this is factorizable as this. I hope you know what's your omega and omega square. Anyways, I'll write it down again. Omega is minus half plus I root 3 by 2, and omega square is minus half minus I root 3 by 2. Okay, don't forget this. Very important. Achha, one more thing I would like to add over here. Don't start taking any omega to be minus half plus I root 3 by 2 unless until stated that it is one of the complex cube roots of unity. Omega could also be used for any complex number in general also, because sometimes, see, it's like the GIF symbol. If I use a square bracket, it may be some normal bracket also. So unless until I say this square bracket is a GIF, don't start using any square bracket as a GIF function or a greatest integer function, right? In the same way, unless until they say omega is a complex cube root of unity, don't start taking omega as minus half plus I root 3 by 2. Okay, many people, whenever the question says there is a complex number omega, they automatically think it's a complex cube root of unity. No, unless until stated, do not take it to be complex cube root of unity. Okay, the same concept you can actually factorize as one more thing. Replace your z with a minus z. Very interesting here. If you replace your z with a minus z, you will realize you have written z square minus z plus 1, and this could be written as z plus omega square. Correct? This tells us something very interesting. It says that z square minus z plus 1 equal to 0 has roots minus omega and minus omega square. Okay, and you will be happy if I just multiply both sides with z plus 1. Okay, that means z cube plus 1 equal to 0. Okay, this has roots minus 1 minus omega square. Please remember this also, it's very useful. Is that fine? Why minus 1 came? Because of this z plus 1 which I multiplied to both the sides. Is it fine? Any questions? Okay. Now, a lateral property that comes out from this entire exercise that we did just now in the last 2-3 minutes is, now we know certain expansion of identities. The first thing that we learned today is that, I think I have to go to the next page. First copy this down, then I'll go to the next page. So these are your, you can say, cube roots of minus 1. You can say these are your cube roots of minus 1. Okay, so if somebody says what are the cube roots of 1, you will say 1 omega square. Omega is half plus I root 3 by 2, minus half plus I root 3 by 2. And omega square is minus half minus I root 3 by 2. If somebody says what is the cube root of minus 1, you will say minus 1 minus omega square. Is this fine? Yeah, mostly we are used to seeing this Madhav as just a -1, but -1 is just 1/3 the answer. There are two more answers which you probably did not know till today. It were these values which you are like missing out. Okay, all right. So going forward, we learned certain related expansions or related factorizations. Till now, if somebody asks you, hey, can you factorize this guy? Okay, you should say, come on, this is not factorizable. But now it is. It can be written as a minus b omega and a minus b omega square. Similarly, you can factorize a square minus ab plus b square, which is a plus b omega, a plus b omega square. Okay, is it fine? So summarizing, if you want to factorize this, it is factorizable as a minus b times a minus b omega times a minus b omega square. Now don't stop at a square plus ab plus b square. Okay, so given that you have learned this, okay, you can apply this to this case, correct? Similarly, I can say a cube plus b cube can be written as a plus b omega and a plus b omega square. Okay, not only that, there is something more coming up. You can also factorize a square plus b square plus c square minus ab minus bc minus ca as a plus b omega plus c omega square times a plus b omega square plus c omega. So these are some interesting factors that you are going to learn today. And this term, which I think most of you already know, this term used to be factorized as a plus b plus c times this term, which is again factorizable like this. Okay, so some important expansions. No need to remember except for the except for this one. This is very helpful. This is used in some of the cases. Done. Copied. Okay. Now I'm not done with the properties. I have a couple of more things to add. Let's say fourth property. Another thing that you would observe is that omega and omega square are basically conjugates of each other. Did you realize that? I think you must have realized. So omega was minus half plus I root 3 by 2. And omega square was minus half minus I root 3 by 2. So of course they are conjugates of each other. Not only that, omega and omega square are reciprocals also of each other. Okay, why? Because omega cube has to be 1, right? So you can write it as omega into omega square equal to 1. So omega becomes reciprocal of omega square and vice versa. And vice versa. Correct? Right? So many important informations we are gathering. Okay. Now there are certain more properties which I want to give you, but I'll give you as a question. I'll give you as a question. Property number, I think 7. 7, I believe, right? Or 7 or 8? 4, 5, 6. 6, 6. Sorry, 6. Okay. I would like you to tell me what is this value. So basically, I'm raising all the roots to a power of p. So what is this value? If p is a multiple of 3 and if p is not a multiple of 3. So what are these question marks? P is not a multiple of 3. Please work this out. You can type out your answer in the chat box. Nobody. Come on, guys. This is easy. Okay. At least we can say that if p is a multiple of 3, let's say p is equal to some 3k, k being some integer. So this is 1 to the power, sorry, this is 1 to the power 3k, this is omega to the power 3k, and this is omega square to the power of 3k, or you can say omega to the power 6k. Isn't this 1? Isn't this also 1? Isn't this also 1? Because you are raising it to a power which is a multiple of 3. So won't this question mark become a 3? Correct? If p is not a multiple of 3, then what will happen? Let's check. See, if you look at these expressions very carefully, they are actually in geometric progression. Okay, so this is a geometric series, you can say. Geometric series with the first term being 1 and common ratio is omega to the power p. Correct? So when you're summing a geometric series, your sum is first term, common ratio to the power of number of terms minus 1 by common ratio minus 1. Right? Geometric series formula. Correct? Now, can I not write this as omega to the power 3 to the power p minus 1 by omega to the power p minus 1? Isn't this guy 1? So 1 to the power p is 1 only. 1 minus 1 by omega to the power p minus 1. Correct? So your answer will be 0. Now many people will say, sir, why not denominator can become 0? Because p is not a multiple of 3. If p is not a multiple of 3, the denominator cannot be 0. This cannot be 0. Okay, so this is 0. So your answer here is a 0. This has come as a direct question in some competitive exams. So please make a note of this. Please make a note of this. Is this fine? Any questions? Any questions? Any concerns? Okay, let's take few questions. Let's take few questions. Okay, let's take this one first. If 3 by 2 plus I root 3 by 2 to the power 50 is 3 to the power 25 times x minus iy, find the ordered pair x and y. Find the ordered pair x and y. Please write your response on your chat, on the chat box. Okay, Aditya, will check. Very good. Anybody else? Okay, Gayatri, very good. All right, guys, let us discuss this. Now, I'm sure you cannot find out this value directly. You cannot, even if you know binomial theorem, it is not possible humanly to find out to the power 50 and simplify this. So there has to be some way out. Now let us look at this term more closely. Okay. If I take a root 3i common, can I say I will get half minus I root 3 by 2? Correct me if I'm wrong. If I take a minus sign also common, I'll get minus half plus I root 3 by 2. Now this is known to be omega. So I have minus root 3i omega. So this term that you see over here, right over here, is actually negative root 3i omega. Okay. Now if you raise this to the power 50, let me do it here. So 3 by 2 plus I root 3 by 2 to the power 50 means you are raising negative root 3i to the power omega to the power 50. By the way, negative sign will have no meaning and this will become 3 to the power 25. I to the power 50 is like I square. Omega to the power 50 is like omega square. Why? See, I to the power 50 is what? I to the power 50 is I to the power 48 into I square. And this is I raised to a multiple of 4, so that has to be 1. Correct? Similarly, omega to the power 50 is like omega to the power 48 into omega square. And 48 is a multiple of 3. So that will be 1 anyway. So 1 into omega square. So I square is negative. Omega square is minus half plus I root 3. Sorry, minus half minus I root 3 by 2. Okay. If you reduce this negative inside, it will become half plus I root 3 by 2. Now compare this with the given expression. So if you compare it, x will become half. So compare this with this. So x will become a half and y will become negative root 3 by 2. This is your answer. Let me check. Anybody got it? Anybody who got it? Nobody got it. Nobody got it. Nobody got it. Small mistake, sign mistake, Gayatri. Pranav also sign mistake. Be careful. They asked x minus iy, not x plus iy. Okay, next question. Okay, this is a big question, but we'll not do everything. Let's probably work on question number. How about doing question number 4, 5, and 6? Let's do 4 first. Let's do 4 first in this, and then we'll go on to the different questions. Let's do 4 first. Done. 4th. Very good, Aditya. That's correct. So Aditya has already cracked the fourth question. Well done. That was good. Good speed. Others, let's discuss it in another 30 seconds. Guys, we'll take one more class to finish this chapter. And one more thing I would like to discuss about your Dashera break. I think I've already discussed. The only holidays that you get is on 25th, 31st and 1st. Okay. If at all your class happens to fall on these days, we will have extra classes to compensate for it. No, today's class is till 9 o'clock, Swaraj. Swaraj is worried. ये कब खत्म होगा? 7:30 only, Swaraj, don't worry. Till when did I have... अरे मत खाओ ना एक दिन डिनर, क्या होगा? थोड़े से पतले तो हो जाओगे. No. Today's class is still 7:30 only. But what I'm trying to say is you will have an extra class in the morning times, one of the days. Okay, so one of the non-Centum days, you'll have a class in the morning time. Okay. So I think first is where you are getting stuck, right? First is a Saturday, right? Anybody who's aware of the calendar? How can you have a class during this Christmas break, Aditya? Don't you have holidays starting from? Let me check my calendar. Oh, yeah. So your classes will not get stuck. So you are safe. 27th will be normal class and 2nd will be normal class. Yeah. But other subjects, if at all you have it, you will have an extra class. All right. So let's discuss this, guys. Long time has been given to this. See, 1 plus omega is, let it be 1 plus omega. 1 plus omega square, let it be 1 plus omega square. Now 1 plus omega to the power 4 is back to 1 plus omega. Why? Because omega to the power 4 is what? Omega to the power 4 is omega cube into omega. And omega cube is known to be 1. So it's back to omega. Okay. Omega to the power 8 is again omega square. Right? Again, the next term would have been omega to the power 16. Omega to the power 16 is again 1 plus omega. So basically this trend continues. Will continue. So since it is continuing till 2n terms, can I say for sure that it will actually result into these two terms repeated n times? So can I say this to the power of n? Okay. Now, we will use the property that 1 plus omega square is 0. So 1 plus omega would be negative of omega square. So this guy will be negative of omega square and this guy will be negative omega. And this is actually omega cube. Omega cube to the power n has to be 1 to the power n has to be 1 only. Option, sorry, not option. Answer for this is going to be 1. Aita? Is that fine? Any questions, any concerns? Okay. We'll do the fifth one. Sixth one, you will not be able to do right now because you're not aware of sequence series summation process. So we'll do the fifth one on the next page. Yeah. Sixth one. Oh, sorry, fifth one, not sixth one. Sixth one we'll do when we do sequence series and progression. No need to do sixth one. Simplify it. Just simplify this. Sir, how do we simplify even this? What? How do I know which is getting cancelled and not? There's actually a trick hidden over here. Look at it very carefully, you'll get the answer. Okay, without much waste of time, see, can I do one thing? Can I write this omega, sorry, alpha into 1? Sorry, I'm just writing the numerator. Okay, what I'll do is I'll write this as omega cube. Right, what I'm doing, I'm writing 1 as omega cube. That is valid, correct? And denominator is, let me write first this term, then beta, then gamma omega, then delta omega. Now take an omega common from the numerator. And there you go, this becomes same as the denominator. Just, here is it, answer is omega. Okay. So these kind of questions can also be asked in some form or the other. So please be careful of that because they all convert into one another. They all keep converting into one another. Okay. All right, let's take another one. This time a slightly complicated one. This I'll do when I'm doing. Okay, let's do this one. I'll put the poll also for this. Very good. I've got one response. Guys, let's close this in another 1 minute. Okay, one more question I wanted to ask. I know some of you will curse me for asking this. Are you prepared for a 4-hour class during during Christmas break? Sir, sir, Maafi sir. Okay. Madhav is saying no. See, because we are terribly behind schedule. We have not even started conic sections, right? Conic section itself is a big chapter. So you have to cover binomial, sequence series, conic sections, principle of mathematical induction, introduction to 3D geometry, statistics, split it into 2-3 hours. Are you ready for 6 hours class in a day? 3 in the morning, 3 in the evening. Sir, बच्चों की जान लोगे क्या sir? Okay, anyways, we'll see. If I keep a longer duration, I'll inform you in the class before that. And I'll give you a longer break. Probably I'll give you 10 minutes break. Okay. Alright guys, चलो जल्दी करते हैं. Time बहुत कम है हमारे पास. Let us do. Okay. See guys, when you see this z square plus z plus 1, it automatically gives you an idea that omega is going to satisfy this, right? Correct? So you can safely put your z as omega in this expression. So let me end the poll first. Most of you have given the answer as C. In fact, all of you have given the answer as C and you are correct also. Let's check this out. How? So z could be put as omega over here. Now, if you look at the first expression, z plus 1 by z square, you're actually writing omega plus 1 by omega square. And remember, 1 by omega is like omega square. Yes, reciprocal of omega is omega square. And omega plus omega square is actually minus 1. So don't forget 1 plus omega square is actually 0. So omega plus omega square is a minus 1. So this will give you a 1. So first term here will be a 1. Okay. If I do z square plus 1 by z square, remember you are writing omega square plus 1 by omega square square, which is nothing but omega square plus omega the whole square, which is actually 1. Okay. Z cube plus 1 by z cube, this will be nothing but 1 plus 1 square, that is actually going to be 4. Okay. Now, after this, the next term that you get, that is z to the power 4, 1 by z to the power 4 square, it is actually omega 4, 1 by omega 4 to the power 2, which is back to omega plus 1 by omega to the power 2, which is same as the first term. So that will also be 1. Correct? And likewise, I don't have to write everything. This will also be 1. But this will be again a 4. So it is like 114, 114, 114 like that. Okay. Anyways, I think we have to only go till this term, right? Yeah. So your answer will be 114, 114. That is nothing but 6 plus 6, 12. Option number C is correct. Option number C is correct. Is it fine? Let's take one more before we close the day. Quite a long day, right? Right now, you'll not be able to do this problem, this problem, this problem. So we'll see this problem. In fact, since time is less, this problem I will do it. You just watch how to do it. Read the question first. Everybody read the question. Alpha, beta, gamma are roots of this equation. Find the value of alpha minus 1 by beta minus 1, beta minus 1 by gamma minus 1, and gamma minus 1 by alpha minus 1. Okay, how to solve this question? Alpha, beta, gamma here need not be real quantities. They can be complex also. Okay. Now see here, this term that you have, I will write it like this. See what I did? This 7 here, I wrote it as minus 1 plus 8. Now why did I do that? It is because this will become x minus 1 cube. Correct? So in short, we are basically trying to solve this equation. Okay. So for the time being, treat this as if you're trying to solve z cube is minus 8. Okay. So what are the cube roots of? So we have to find out the cube roots of this guy. Okay. So there are a lot of ways to do it. You can treat as if you have written 8 to the power 1 by 3 minus 1 to the power 1 by 3. So 8 to the power 1 by 3 is 2. And this guy can be written as, these guys can be minus 1 minus omega, and minus omega square. Okay, so the answer that you get for cube roots of 8 will be these three. So these will be your roots, which is actually minus 2 omega, and minus 2 omega square. Okay, but this is your this value. You have to find x value. So they are actually x minus 1 values. So x value will be minus 1, 1 minus 2 omega, and 1 minus 2 omega square. So this minus 1 I have sent it to the other side. Okay, so you can call any one of them as alpha. Let's say I call this as alpha, I call this as beta, I call this as gamma. Now what do I need? I need alpha minus 1 by beta minus 1, beta minus 1 by gamma minus 1, and gamma minus 1 by alpha minus 1. Let's start putting the values. Alpha minus 1 will be minus 2. Beta minus 1 will be minus 2 omega. Okay, correct. Let us simplify this. This will be 1 by omega. This will be also 1 by omega, and this will be omega square. 1 by omega itself is omega square, omega square, omega square. So the answer is 3 omega square. That is nothing but 3 times minus half minus I root 3 by 2. So the answer would be minus 3 by 2 minus I 3 root 3 by 2. This is going to be your answer. Okay. That depends upon what option is given. They may give you an option in terms of omega only. So here I use a bit of transformation of an equation. If you want, I can explain this again. So what I did first was without breaks. See, break is not for the student. Let me get this clarified. Break is for the teacher. Because normally I keep speaking for 3 hours, right? You try speaking for 3 hours. Next day probably you won't be able to talk also. Break is for the teacher, not for the student. No. Okay, Madhav, if you was your camera is off, you're sitting and having your food, how will I come to know? But as a teacher, I cannot eat and speak at the same time, right? Okay. So yes, of course I can drink water, but I need to eat something, correct? So break is always for the teacher, not for the students. So that break is important. Okay, so I'll explain this. This is actually x minus 1 cube plus 8. So if you bring the 8 to the other side, it becomes this. So what I did was I assumed z to be x minus 1. So let z be x minus 1. So basically it became an equation like this. And this you can easily solve by using our de Moivre's theorem. Or I've given you another alternative way to look at it. Minus 8 to the power 1/3 can be treated like this. Okay. 8 to the power 1/3 will be 2. Now many people will ask me, sir, 8 to the power 1/3 itself can have 3 roots. Of course, but you will see that many of the roots will come out common, right? So there will be an overcounting of roots in that case. So 3 from here, 3 from here, you will get more roots than required. There will be repetition of roots. So that's why you don't have to take repetitions here. Okay. So your roots will become minus 2 omega minus 2 omega square. But remember, this was z value. Z was x minus 1. So x will be, just add a 1 to each one of these terms. Okay. And call them alpha, beta, gamma. Place it over here. Simplify. Your answer is there. Okay. Next class, we are going to talk about something very, very important and something very, very complicated also. Next class will be a slightly complicated class on complex numbers. Sir, this was already complicated.